Welcome to ODEs Lesson 32, Power Series Solutions of Non-homogeneous Linear Initial Value Problems. Our goal is to find a power series solution to a non-homogeneous ordinary differential equation and also an initial value problem. We'll use Euler's method to find a numerical solution to the same initial value problem, and we'll compare the two solutions graphically. This is the initial value problem we want to solve. The differential equation y double prime plus 2xy prime minus x squared y equals e to the minus half x. The initial conditions are y of 0 equals 2 and y prime of 0 equals minus 1. So with this differential equation, second order, and these two initial conditions, that forms our initial value problem. Let's look at a general fact about solutions to this second order differential equation. Let's suppose that a, y0, and y1 are numbers. The a, y0, and y1 are in these initial conditions. Consider the initial value problem, this differential equation, for y of x, and it has three functions in it, p of x, q of x, and f of x. If p of x, q of x, and f of x are continuous on an open interval I, and this number a is in I, then the initial value problem has a unique solution on that interval I. It's represented schematically like this. On the x-axis, here's the number a. There is some interval I here containing a, such that this problem, this initial value problem, has a solution, and it is a unique solution. Let's look at this initial value problem. This will be the problem we'll solve in this lesson. The differential equation y double prime plus 2x y prime minus x squared y equals e to the minus half x. Y of 0 is 2, y prime of 0 is minus 1. If we look at this, the function 2 of x, which we'll call p of x, is continuous on minus infinity to infinity. Minus x squared is also continuous on minus infinity to infinity, as is e to the minus 1/2 x. 0 is in the interval from minus infinity to infinity. So that last result tells us that this initial value problem does have a unique solution on the interval from minus infinity to infinity. There is one and only one solution to this initial value problem on that interval. Let's recall this fact. If I have a power series that equals 0 for all x in the neighborhood of this x0, where this series is centered, then all of the c sub k's that appear here have to be 0, which means that the only way to write the 0 function this way is the sum k goes from 0 to infinity, 0 times x minus x0 to the k. Let's start substituting y equals the sum k equals 0 to infinity c sub k x to the k into this differential equation. We'll start with y double prime. Y double prime is the sum k goes from 0 to infinity, k times k minus 1, c sub k x to the k minus 2. And the k equals 0 and the k equal 1 terms are going to be zeros. So we can start this sum at k equals 2. And then we can re-index this. Instead of going from 2 to infinity, we'll go to 0 to infinity, and we'll replace all the k's here by k plus 2's, and we get the sum k plus 2, k plus 1, c sub k plus 2, x to the k. Let's pull out the first two terms of this infinite series, and we get 2c2, makes you want to square dance, plus 6c3x, plus the rest of the terms, k equals 2 to infinity of this stuff, just rewritten here. Now let's move on to the 2xy prime term. 2xy prime is 2x times the power series for y prime, and that turns out to be the sum k equals 0 to infinity, 2k c sub k x to the k. If you think about it for a second, y prime is just going to be k c sub k x to the k minus 1, but then you're multiplying that by 2 times x, so we finally get this. Now, once again, let's take out a term from this. The k equals 0 term is obviously 0 because we have a k factor here. The k equals 1 term is going to be written out here. 2 times 1 times c sub 1 x to the 1 is just 2c1 times x, plus the rest of the terms. The sum k goes from 2 to infinity of this stuff. Now let's move on to this term. We're still letting y be this power series representation of y, and we're looking at x squared y. So we're just going to multiply this by x squared. X squared times x to the k gives us x to the k plus 2. So x squared y is the sum k goes from 0 to infinity, c sub k x to the k plus 2. Now we will re-index this. Instead of letting k go from 0 to infinity, let the sum go from 2 to infinity, and we'll replace all the k's with k minus 2's. So this k becomes k minus 2. Up here, this exponent k plus 2 just becomes k. So now we are up to this term in the equation, e to the minus half x. Well, let's remember that e to the x is the sum of x to the k over k factorial. So what we're going to do is take that well-known power series and replace the x with minus 1/2 x. So we get the sum, k goes from 0 to infinity, 1 over k factorial times minus 1/2 x raised to the k power. Now, we can simplify this just a little bit. We can write it as minus 1 to the k from this minus this 1, this k, times 1 actually. Okay, and then in the denominator, we're going to have a 2 to the k, which is here. We have a k factorial, which is here. And we also have a factor of x to the k, which is here. Now, once again, let's write this slightly differently for ease of computation. Let's take out the first two terms from this series, and then write the rest of them, k going from 2 to infinity. The k equals 0 term here turns out to be 1. The k equals 1 term turns out to be minus 1/2 x, and then the rest of the terms are here. Let's see what the initial conditions in the initial value problem give us. Remember that y of x is this infinite series. If we plug a 0 into this formula, y of 0 is just going to be c sub 0 times 1, and that gives us that c sub 0 equals 2. If we differentiate this with respect to x, the first term, the constant term, will be 0. the derivative of c sub 1 x to the 1 is just going to be c sub 1. And the rest of the terms will have powers of x in it. So if I let y prime of 0 equal the initial value minus 1, that tells us that c sub 1 is equal to minus 1. So plugging this power series into this differential equation, we get the y double prime terms that we saw before, which are these in black, the plus 2xy prime, which comprises these two terms, minus x squared y, which is this term right here, minus e to the minus 1/2 x is this stuff, just the expansion of that exponential function, and so this equals 0. Okay, so all the powers of x have to be 0. So if we look at this, the only constant term here is this 2c2 and also minus 1 here. So 2c2 minus 1 equals 0. Solving, we get c sub 2 equals 1/2. Now what about the x term, the coefficient of the x term? We have a 6c sub 3x here. We have a plus 2c sub 1x here. And we also have a minus 1/2 x here. And so that gives us, for the coefficient of x, 6c sub 3 plus 2c sub 1 minus a minus is plus 1/2 equals 0. And solving this for c sub 3, just subtract these two terms from both sides, then divide both sides by 1/6. So c3 equals this stuff. But let's remember that c sub 1 we found out by initial condition was minus 1. So we substitute that in, simplify, we get c sub 3 has to be 1/4. Now the higher power terms, the coefficients of those higher powers looked like this. These had to equal 0. This was our recurrence relationship. If we solve this for c sub k plus 2, just do some simple algebra, we get c sub k plus 2 is 1 over k plus 2, k plus 1 times this stuff. And this is going to hold for k greater than or equal to 2. So we know what C0 and C1 were from the initial conditions. Here we know what C2 and C3 are. And for k greater than or equal to 2, this is going to give us C sub 4, C sub 5, and all the rest of the C values. So here's what we have seen so far. We have this differential equation equals e to the minus 1/2 x. We're going to look at power series of this form, and we found out from the initial value problem that C0 was 2, C sub 1 was minus 1, C sub 2 was 1/2, C sub 3 was 1/4, and this equation here is our recurrence relation. So at this stage, we know C0, C1, C sub 2, C sub 3, and by the recurrence relationship, we know C sub 4, C sub 5, and so on. So we basically know all of the C sub k's. We're going to approximate the solution function by a function f. So y of x will be approximately equal to f. A list including that has those c values in it, and num coefficients tells us how many terms we're going to use in our partial sum, approximating the infinite series for y of x. And so it's given by this formula. Sum k goes from 0 to whatever the number of coefficients are, or maybe the number of terms would be a good thing to call this, c sub k times x to the k. Over here is a function, that will do this for us. It's very similar to one that we saw in a previous lecture. We just have a comment here telling us that this function will compute a partial sum approximating y of x. So we define f of these three parameters to be the following by this code here. I'll first set sum equal to 0, and then here with these two lines we have a for loop. For n in the range num coefficients, so that means that n will take on the values 0, 1, 2, all the way through num coefficients minus 1. I'm going to look at c sub n times x raised to the nth power, and I'll add that to whatever the previous sum was. We started with sum equal to 0, and from that starting point we start adding terms like this to the sum, and when this loop finishes we return the value of sum, which is the value of this series, this partial sum up here. So this just defines f. This is not the whole function. Our function is going to call f. Our main program will call the function f to get points that we can plot on a graph. So here's the main program, and this can be put in one file right after that function. So we'll set the number of coefficients equal to 40, and C, my list of coefficients right now starts at 2, minus 1, 1/2, and 1/4. And then for k in the range from 2 to number of coefficients, I'm going to, by that recurrence relationship, calculate more values of C for this list using that recurrence relationship, and I'll append it to the list C. So when this little for loop ends, we're going to have this C list have values of C0, C sub 1, C sub 2, C sub 3, all the way through C sub 39. Print C, which I'm not going to show the result of that here, but for debugging purposes, we can print that list to see what they look like. And then we're going to build up x versus y values in two lists, and that's what we're going to plot. So we'll set the number of points equal to 50. I'm going to plot 50 points along this curve. Delta x will be 2 divided by the number of points. So in this case, it'll be 2/50ths. For k in the range of number of points, x will be 0 plus k times delta x. I'll append that value of x to x list. I will calculate a y value using that value of x, the coefficients that we have, and the partial sum will have 39 terms in it. And then whatever this y value is, we'll append it to y list. And after this for loop ends, we will have lots of points to plot. And we have here plt.plot x list y list. Plot is in a plotting library. And if you look at the previous slide, you'll see that we included a library and we just called it PLT for short so that we could call this plot function. The graph that we get looks like this. So this is pretty close, I suspect, to what the graph of the solution to the initial value problem looks like. There's always a chance that there's some numerical error or programming error, maybe a typographical error. So it'd be nice to check to see if that solution seems right. And one way to do it is to calculate the solution a different way. So we're going to use Euler's method to determine if that solution we just saw looks reasonable. Euler's method is based on a tangent line approximation, and we'll use that to generalize it to a system of two first-order ordinary differential equations equivalent to our second-order ordinary differential equation. So we're going to be looking at a system of two equations in two unknown functions. So first of all, let's just talk about the tangent line approximation again. We saw this in a previous lesson. We can approximate the derivative of f at x by f of x plus h minus f of x over h. And so that means that f of x plus h, for h small at least, and we're talking about f being differentiable obviously, is going to approximately be equal to f of x plus f prime of x times h. This equation can be gotten from this formula up here, just solving it for f of x plus h. Okay, so just to change our notation a little bit, y of x plus h is approximately y of x plus y prime of x times h. And so here's the discrete approximation we can make. Let's let k be some integer. Let's let x of k plus 1 equal x of k plus h. Let y sub k plus 1 be y sub k plus the derivative of y with respect to x at x sub k times h. This formula right here is a discrete version of this formula up here. And we're going to realize that y sub k plus 1 is our approximation for y evaluated at x sub k plus 1. And so we have a number line here, an x-axis, let's say, with points x0, x1, x2, x of 3 through some x sub n. And the length between, the distance between adjacent x sub i's, the length of this little subinterval is h. In a graph, the situation looks as follows. Suppose that here is the function f of x, or y of x, whichever we want to call it. And on this curve, we have a point, x sub k, y sub k. If we find the tangent line to this curve at this point, here it is, and if we move over a distance h horizontally, we get another point on this tangent line, and this has coordinates x sub k plus 1, and I'm just going to call it y sub k plus 1, which is this thing right here, or more accurately, this one down here. So this is a discrete approximation to the y value for this x value on the curve. Notice that this point is actually on the curve, and for a small value of h, this point is still going to be pretty close to the actual solution curve. And that shows us why this solution approximation makes sense. Let's use Euler's method to numerically solve the following initial value problem. Y double prime plus 2xy prime minus x squared y equals e to the minus half x. Y of 0 is 2, y prime of 0 is minus 1. We have a second derivative here, a first derivative of y, and y itself. We're going to see that we can change this second order differential equation into a system of two first order differential equations. So here's what we'll do. First of all, let's let w equal y, and let z be the derivative of y with respect to x. Well, in that case, if we differentiate this with respect to x, we get the derivative of w with respect to x is the derivative of y with respect to x, but the derivative of y with respect to x is equal to z. On the other hand, if we differentiate this second equation with respect to x, we get the derivative of z with respect to x equals the second derivative of y with respect to x. Okay, so I want to use these substitutions to change this second order equation into a system of first order differential equations. Before we look at these too carefully, let's look at each of these. The derivative of w with respect to x equals z, that's a first order equation. And the derivative of z with respect to x equals x squared w minus 2xz plus the exponential of minus a half times x. This is also a first order differential equation. So now what we want to see is why these two equations give us this second order equation. Well, let's look at this for a minute. The derivative of z with respect to x, that's the second derivative of y with respect to x. Okay, and so here we have the second derivative of y with respect to x equals x squared times y, which is basically what we have here if we move stuff to the other side. And then minus 2x dy dx, and that's this one taken to the other side, minus 2x, the derivative of y with respect to x, plus the exponential of minus 1/2 x, which is right here. So we see that this equation is first order, but it's first order because this z here was the derivative of something, and so this derivative of z with respect to x is the same as the second derivative of y with respect to x. And so basically we have a relationship between y and w. We have a relationship between z and the derivative of y also. And we have a relationship between the derivative of z with respect to x and the second derivative of y. So here's what we're going to do. We're going to pick a small h greater than 0, and for the initial conditions that we have up here, I'm going to let x naught equals 0, which is the value of x in these two initial conditions. W naught, well, w is y, and so basically y naught, which is w naught, is going to be 2. Z naught equals minus 1. Z is the derivative of y with respect to x, and so z naught is going to be the derivative of y with respect to x evaluated at 0, and it's minus 1. That corresponds to y prime of 0 equals minus 1. Okay, so excuse me. So now we have these equations, and we want to numerically approximate the solution using Euler's method. So let's see what this iterative method is going to be. First of all, we start with x naught, remember, and we're going to define x sub k plus 1 to equal x sub k plus h. So for instance, x sub 1 is x naught plus h. X sub 2 is going to be x sub 1 plus h, and so forth. Let's look at w sub k plus 1. W, remember, is equal to y. And so we're going to do about the same thing that we did in the tangent method. W sub k plus 1 equals w sub k plus h times the derivative of w with respect to x. But wait a minute. The derivative of w with respect to x is just z, isn't it? Okay. Z sub k plus 1 is going to be z sub k plus h times the derivative of z with respect to k. But wait a minute, the derivative of z with respect, I should have said x, the derivative of z with respect to x is given by this stuff over here. And so for this, we'll substitute that in. So z sub k plus 1 is z sub k plus h times all of this. Okay? Now, at the end of a loop in a program that does this sort of stuff, let's see, the w's correspond to the y's, and the x's correspond to themselves. So what we want to do at the end is we want to plot x versus y, and so in this scheme we'll be plotting x versus w. Okay, so let's see, what does this Euler's program look like? First of all, we're going to let w naught be 2, so I'm going to create a list with just one element in it for w, 2. We'll create a list for z, which just consists of one number, minus 1. That corresponds to z naught equals minus 1. X equals 0 corresponds to x naught equals 0. Remember when you have lists here, this is the 0th element of the list w. This is the 0th element of the list z, and so forth. As time goes on, we're going to increase the length of these lists. The h that we saw in this algorithm, like right here, we're going to set that equal to 0.01. So now we'll do the following. For k in range 200, so that means for k going from 0 through 199, I'm going to add an element to the x list. X dot append x of k plus h. That corresponds to what we have up here. X of k plus 1 is x of k plus h. W dot append w sub k times plus h times z sub k. That's what we have right here for w sub k plus 1. To the z list, we append z sub k plus h times, and then all this stuff, which is what we have right here, z sub k plus h times all of this stuff. Then after this loop executes over and over about 200 times, then we will plot x versus w. That's the same as x versus y. And so this will be a plot of our approximate solution to the initial value problem. So here is the program using Euler's method that we just saw. When we execute this program, this is the graph that is produced by this plot statement down here, plot x versus w. And we see it starts at 2 here. So y of 0 is equal to 2. Y prime of 0 was minus 1. And if we look at this, the slope here looks like it's probably about minus 1. Okay, so this is the output from this numerical approximation. So now let's compare the two approximate solutions to that initial value problem. We used a partial sum from the power series solution to that initial value problem to generate this graph, and we used Euler's method to generate this graph for the same initial value problem. Power series versus Euler. If you look at these fairly carefully, it's very hard to see any difference between these two curves. They both start at 0, 2, and the graph of these end up here. And notice that the vertical axes are the same, and they end up at about just the same height here, I guess. So visually, at least, they appear the same. It might be interesting to take the difference of these two approximate functions and see how close it is to 0 for all terms, but we're not going to do that right now. So what did we accomplish in this lesson? Well, we found a power series solution to an initial value problem with a non-homogeneous ordinary differential equation by the power series method, substituting an arbitrary power series into the equation. And we found power series for y prime and y double prime by differentiating the power series for y term by term. And so we solved the problem using power series. We also solved that same problem using Euler's method, which is basically a tangent line approximation. And we found a numerical solution to the same initial value problem using a pretty small value of h. In a way, the smaller the value of h you use, the more accurate your approximation to the solution becomes. But since we're doing it on computers, we also have to worry about round-off error, truncation error, those sorts of things. So if you make h too small and do, let's say, millions of calculations to calculate the next point on the graph, errors can add up and your resulting graph can be way off. So there has to be a trade-off. You don't want h to be too large, and you don't want h to be too small. In this particular problem that we looked at, we compared the two approximate solutions and found that their graphs, at least visually, appeared identical. Well, I hope you enjoyed this lesson. Thank you for watching it, and please stay tuned for more. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.